Welcome to G Fun Facts Online. If you were to look at the universe with eyes that could see gravity instead of light, the night sky would be unrecognizable. The familiar spiral galaxies and glowing nebulae we admire in telescope images would appear as mere specks of dust floating in vast invisible oceans. These oceans are made of dark matter, a mysterious substance that outnumbers visible matter 5 to 1. It holds the Milky Way together, preventing the stars at its edge from flying off into the void, and it acts as a cosmic lens, bending light from distant quasars. For decades, this invisible architect has been the subject of a singular, dominant theory regarding its temperature. The standard cosmological model has rested on a chilly assumption that dark matter was born cold. In the specific language of cosmology, cold does not just mean frigid, it means slow. To build the intricate cosmic web of galaxies and clusters we see today, dark matter particles had to be sluggish enough to clump together under gravity. If they were hot, meaning they were zipping around at relativistic speeds, they would have streamed out of primordial gravitational wells, smoothing out the universe like a blurred photograph. This cold dark matter, or CDM hypothesis, became the absolute dogma of physics because it fit the data remarkably well. It predicted the fluctuations in the cosmic microwave background and explained the large-scale distribution of galaxies. However, cracks have appeared in this frozen FA8. New theoretical breakthroughs and breaking news research from early 2026 suggest a radical alternative. Dark matter may have been born red-hot, zooming at nearly the speed of light in the universe's earliest moments, only to cool dramatically, just in time to seed the galaxies we see today. This revelation challenges the so-called WIMP miracle, resurrects discarded theories, and forces us to rethink the violent, fiery first seconds of the cosmos. To understand why this shift is happening now, we have to look at the history of the hunt. For the last 40 years, the prime suspect for dark matter was the WIMP, or weakly interacting massive particle. Theoretical physics, specifically supersymmetry, naturally predicted particles that were 100 to 1,000 times the mass of a proton. Because they are heavy, they would become slow very early in the universe's history. This allowed them to clump gravitationally on all scales, from tiny dwarf galaxies to massive clusters. This cold dark matter model worked beautifully for large-scale structure. It was fueled by a coincidence so elegant it was named the WIMP miracle. In the early universe, particles were being created and destroyed constantly in a hot plasma. As the universe cooled, this creation stopped. When physicists calculated how many WIMPs would be left over from this thermal freeze-out, they found that if a particle interacted via the weak nuclear force, the amount remaining today would be exactly the amount of dark matter astronomers observe. This drove billions of dollars of investment into detectors like LUX-ZEPLIN, Xenon, and PANDAX. But by 2025, the WIMP miracle had begun to sour. Despite detectors sensitive enough to spot a mosquito bumping into a neutron star, we saw nothing. The parameter space, which is the range of possible masses and interaction strengths for WIMPs, was being colored in with excluded labels. Furthermore, on small scales, inside individual dwarf galaxies, the cold dark matter model predicted structures that we simply did not see. It predicted that the centers of galaxies should have a sharp spike or cusp of dark matter density, but observations showed a flat core. It predicted thousands of tiny dwarf galaxies orbiting the Milky Way, but we only see about 60. These are known as the cusp-core problem and the missing satellites problem. Enter the new paradigm from 2026. A groundbreaking study from researchers at the University of Minnesota and Université Paris-Saclay has shown that our assumption of cold dark matter was too rigid. Their work focuses on a specific, chaotic period in the early universe called reheating. To understand this, we have to rewind to inflation. Before the standard hot Big Bang, the universe underwent a period of exponential expansion called inflation, which smoothed out space. Inflation ended when the energy driving it decayed into standard particles, a moment called reheating. This is effectively when the hot soup of the Big Bang was cooked. Standard WIMP theory assumes dark matter froze out long after reheating was over, when the universe was already in a steady thermal state. The new study asks a different question. What if dark matter was produced during the chaos of reheating itself? During this violent epoch, high-energy collisions were happening as the inflation energy decayed. The researchers found that dark matter particles could be produced in these collisions moving at ultra-relativistic speeds, close to the speed of light. They were, effectively, born red-hot. In the standard view, this would be a disaster because fast particles erase structure. But the researchers discovered a loophole. Because this happened so early, during the transition from inflation to the radiation-dominated era, the universe was expanding in a specific, rapid way. This rapid expansion acts as a brake. If the coupling or interaction strength of these particles is just right, they stop interacting while still hot. However, because they are born so early, they have billions of years of cosmic expansion to slow down before the era of galaxy formation begins. Essentially, the universe stretches their wavelengths. A particle born moving at light speed a tiny fraction of a second after the Big Bang will have its momentum redshifted away by the expansion. By the time the universe is a few 100,000 years old, when structure starts to form, these red-hot ghosts have cooled down enough to behave exactly like cold dark matter on large scales. This mechanism bridges the gap. It allows for a particle that is lighter and more weakly interacting than a WIMP, yet does not ruin galaxy formation like a neutrino would. This brings us to the physics of freeze-in versus freeze-out. To appreciate the elegance of this new model, we must distinguish between the two main ways the universe manufactures dark matter. The WIMP method is thermal freeze-out. Imagine a crowded party in a shrinking room. People are shaking hands constantly. As the room expands and cools, people move further apart and eventually stop finding each other. The number of handshakes freezes out. This assumes dark matter was in equilibrium with normal matter. The alternative is thermal freeze-in. Imagine a party where the guests are incredibly shy, known as feebly interacting massive particles, or FIMPs. They never talk to each other. However, occasionally a normal person might spontaneously turn into a FIMP. Because FIMPs interact so feebly, once they are born, they just accumulate. The newborn red-hot scenario is a hybrid. It suggests a non-thermal or semi-thermal history. The particles interact enough to be produced energetically during reheating, but decouple so early that their velocity distribution is skewed. They are hot remnants that cool effectively. This opens up a Goldilocks zone in parameter space that detectors have not looked at yet. This model is incredibly attractive because it potentially solves the small-scale crises that plagued the cold dark matter model. Remember the missing satellites and the cusp-core problem? If the dark matter was born hot, it might retain just enough residual velocity or pressure to resist packing tightly into the center of galaxies. This naturally smooths out the sharp cusp into a flat core. Similarly, the free streaming of these initially hot particles would have been just enough to wipe out the very smallest clumps, the missing satellites, while leaving the larger ones like the Milky Way intact. It provides a dial that physicists can turn. By adjusting the reheating temperature and the particle mass, they can tune the warmth of the dark matter to match observations perfectly. So if dark matter was born red hot, how do we find it? This is the billion-dollar question. Detectors like Lux Zeppelin are reaching their neutrino floor, where they start detecting neutrinos from the sun that mimic dark matter signals. If they do not find WIMPs soon, that window closes. The red-hot dark matter is likely lighter and interacts more feebly than WIMPs, making it invisible to these tank-based detectors. Instead, the hunt is shifting toward wave-like detectors and quantum sensors. Lighter dark matter acts more like a wave than a billiard ball. New experiments using superconducting qubits and Bose-Einstein condensates are being designed to detect these light dark matter waves. For example, the ADMX experiment uses strong magnetic fields to convert axions into microwave photons, while DM radio listens for the electromagnetic hum of dark matter passing through a circuit. However, the most promising way to confirm the born red-hot theory is not in a basement, but in the sky. Astronomers are looking at the Lyman Alpha Forest. By analyzing the light from distant quasars as it passes through gas clouds, they can map the clumpiness of the universe on small scales. A red-hot history leaves a distinct fingerprint, a suppression of structure below a certain size. Furthermore, future radio telescopes like the Square Kilometre Array will look at the dark ages of the universe before the first stars formed. The temperature of the hydrogen gas in that era is extremely sensitive to how dark matter behaves. If dark matter had thermal energy, it might have warmed the gas slightly, leaving a signal we can detect. Finally, there are gravitational waves. The chaotic period of reheating, where these particles were born, was violent. It likely generated ripples in spacetime. While LIGO currently detects merging black holes, future space-based detectors like LISA, or the Einstein telescope, could hear the hum of the universe's reheating phase. Correlating this hum with the properties of dark matter could prove the theory. As for the candidates themselves, the Axion is the rising star. It is extremely light, solves a major problem in nuclear physics, and fits well with non-thermal production mechanisms. While standard theories predict axions to be cold, high-energy reheating scenarios could produce a hot population. Another candidate is the sterile neutrino, a heavier cousin of the neutrino that does not interact via the weak force. The red-hot study breathes new life into sterile neutrinos, providing a mechanism to produce them in the right abundance. We may even be dealing with a dark sector, a whole dark standard model with dark protons and dark forces that only interact with themselves. The red-hot plasma could have been a dark plasma that decoupled from our visible universe very early on. In conclusion, the universe is proving to be far stranger than we thought. For a long time, we projected our desire for simplicity onto the cosmos. We wanted dark matter to be a WIMP, a single, elegant particle that solved all our problems and showed up right where we expected it. The universe has politely declined that request. The theory of a ghostly mass-born red-hot is a paradigm shift. It acknowledges that the early universe was a complex, dynamic, and violent environment. It bridges the gap between the physics of the very small and the physics of the very large. If this hypothesis holds true, it means that the cold, dark skeleton of our cosmos was forged in fire. The galaxies we inhabit, the stars we orbit, and the gravity that anchors us are the cooled embers of a primordial inferno. We are not just looking for a particle, we are looking for the thermal echo of creation itself. As we move through 2026, with new results from the Large Hadron Collider and new quantum sensors coming online, we may finally be close to unmasking the ghost. Whether it is a WIMP, an axion, or a relic of a red-hot Earth, one thing is certain: the dark universe is finally coming into the light. Thanks for listening to G Fun Facts Online.